Welcome back to Machine Learning class. Today we're going to continue to learn the topic modeling, its concepts. If you remember in the last class, we talked about the probabilistic topic models can assign topic distributions to documents. As observable inputs to the algorithm, we got the documents. Each document has a lot of words, text data in it. Then the algorithm will figure out the hidden structures in the documents. The hidden structures includes how each document contains different proportions of topics, and also for each topic, what are the words and their probabilities within that particular topic. Those two are hidden structures, as we can see here. With the machine learning topic model method, there's no need for human to label the data. The algorithm will figure out the hidden structures. So move on. Now we kind of realize the definition of topic is really a collection of words, and different words has different probability or have different weighting in a certain topic. If certain word has higher probability, that means that word is more common for certain topic. And in humans, common sense, we may think this kind of word as a keyword. Anyway, so topic by definition in the topic modeling is really a distribution over words. And what we ultimately want to answer is, for each document in the collection of documents at hand, what are the distribution of topics? One verse, topic 1, topic 2, up to topic k, if we define the k as an integer. And also, again, we need to actually ultimately also need to know for each given topic, what is distribution of words? From the observable inputs to the hidden structures, we have to apply certain math. That's what the algorithm is about. Actually, there are different math to get there, different mathematical methods to get there. In this class, we're going to discuss and learn latent Dirichlet allocation as the method, for short LDA. In the LDA, the topic distribution is assumed to have a sparse Dirichlet prior. What that means is, first, prior. Prior is the assumption of the probability distribution before any evidence is taken into account. And Dirichlet is one type of probability distributions are commonly used as the prior distribution. And what the sparse means here is really, it means two things. First, it means for each particular document, only small number of topics are included. And then for each particular topic, only small set of words carry the meanings or are often used in that topic. And that's what the sparse means. There are parameters, two parameters to control the Dirichlet prior distribution. They are alpha and beta correspondingly, and we'll see that later. And in practice, we often set the alpha less than 1 and a beta and much less than 1. So that kind of setting will provide us the sparse prior for Dirichlet distribution. The reason that the sparse Dirichlet prior distribution worked is, actually in reality, you probably also realize that is, even though the English may have several thousands commonly used words, but you can imagine that for a particular topic, you probably often can see only a small handful common words which we realize as keywords under the human's intuition. Similarly, when we have a document, have an article, even though in the whole world you may say we have 100, even 1,000 different topics, but you often see that in each particular document, probably only a small set, a few, maybe several topics are discussed in the document, particularly if the document is not a very long one. So the sparse is kind of line up. This kind of assumption is kind of line up with reality pretty well. So that's why the sparse Dirichlet prior and the LDA method works pretty well as a topic modeling method. All right, we're coming to this familiar picture again. But here the point is, before we run the LDA algorithm or the modeling topic modeling algorithm, we typically have to go through the pre-processing step. And typically the text pre-processing steps include those following steps, and we'll go over one by one quickly. And in this process, we're going to use the following three sentences, which are the news headlines we discussed in our last session as example. And basically three documents and three news headlines. All right, the first step is tokenization. What the tokenization means is we want to split the sentence into single terms, into tokens. If we're using Python, you can imagine this task can be easily done by convert the sentence, split the sentence into a list. In the list, each element here, as we can see, each item in the list is a single word or something around this word in the previous sentence. And this is before the tokenization, and this is after the tokenization. This step is pretty straightforward. Just convert the words, the words in sentence into tokens. The following three steps, we just combine them together. Case conversion, pretty simple. Convert all the cases to lowercase. And the next one is remove stop words. What are the stop words? Well, stop words are the frequently used words but do not carry a lot of meaning, such as you may say the, and, or a lot in any sentences or any documents. But those words do not carry a lot of good information in our purpose, which is to identify the topics in documents. So we want to remove those words because they are not so useful. And the next one is remove punctuations. This is also very straightforward. Punctuations, you can imagine, they are not good carrier for the topics, so we do not need them. After doing this, we are getting to just something like below. Everything is in lowercase, no punctuation, and there's no stop word. This is before, and this is after. The next step is stemming. Stemming just like to make words kind of comparable to each other. We know in English sometimes even same word on the different tense or a singular versus plural, the same word may show as different forms. So stemming is kind of cut off the ending part so that remove the different forms, different variations due to the tense or plurals. Again, the reason we're doing this is for the topic modeling purposes, the tense of the plural versus singular does not really give us a lot of good information, even though tense or plural singular in the common daily English, in English writing or speaking, in reality has good usage, but not for our purpose, which is the topic modeling. And this is what we get. For instance, you may notice that this word was floats, and this was declaring. Since we're doing the stemming, and now they just become float, and we also cut off what's in end and become this. This is what they are before, and this is what they are after. Also, one thing to declare is I'm just making some example for illustration. I did not really go through or run the stemming algorithm procedure to do this task. So this may not be exactly identical to a certain programs which handles stemming. This is just for your as examples for your information about having an idea what the stemming is about. After going all the previous steps, now we just want to convert the sentences or the documents, multiple documents into the matrix format. In this matrix, if you look column by column, each column represents unique words, and each row, one by one, represent individual documents. And then row and column combination shows you for a particular document how many times certain words are used. And by now, all the words are unique words. So we are really just kind of count the number of the counts of unique words in each document. Each document itself is on one row. Now here again for illustration, let's see. After we're doing the tokenization and all the remaining pre-processing steps on the previous page, and now we're doing the vectorization, which gives us a matrix. And now after doing all this, we identify there are actually only n unique words, and you can see them like as columns one by one. Then we have d number of documents, and as example on the first row here is showing that the document one have two instances of using first word one, and one instance of using word two, and 0 for word 3, and 1 for the last word n. And so I think you get it. This just kind of count of how many times each unique word is used in each document. So that's called document term matrix. Doing this just that all the presentation, all the representation of the information of text data across all the documents are easily for computer to process. All right. Now, since we just mentioned, now there are only n words are unique, and those n word defines the whole vocabulary or the corpus for task. And all right. So after having finished all the text pre-processing steps, now we come to the topic modeling part, the math part. Again, the topic modeling task need to figure out the hidden structures. One is, the question is, for each given document, what are the topic distributions? And then given each topic, what are the word distributions? So we need to use math. In our case, use LDA to figure it out. And here is how the algorithm works. LDA algorithm works on a high level. Again, there are different math to get those two hidden structures, but we're going to talk about the LDA and more specifically the collapsed Gibbs sampling methods of LDA implementation. So let's see, we have D, the uppercase D documents in total, and each document is to be allocated across K topics, and K is an integer. So that's what we have, and that's what we want to do. Now, this particular method, Gibbs sampling, collapsed Gibbs sampling, is just one way of doing the math, and it has the following steps. The first step is initialization. It doesn't do much. It just goes through every word in all the documents and randomly assign into one of the K topic categories, just randomly. Actually, by doing this random step, because each word in all the document already has a topic category, we already can figure out this probability and this probability. But as you can imagine, because everything here has been assigned randomly, you can compute those probabilities, but they are not the right answer. Now, the following step will do iterations. And the purpose of iterations is we'll go over the word one by one, again, many times until we got stable results. And in those process, we actually revisit the topic category assignment for each word in each document for many times. In the end, if the outcome becomes stable, we'll not be able to have a lot of changes to the topic categorization assignment to the individual words, because it kind of converges to the optimal answer, converge to the right answer. Then we stop there. So basically, we need to make enough number of iterations. And here is what we do. Within each iteration, we go through all the documents. See, this kind of in the Python format, syntax again. So we go through all the documents, and let's see, the current one, particular one working on is document D, lowercase d. And then in each document, we also go through all the words. And currently, we're at word W in the document D. Now, what we do is we assume we do not know the topic assignment for this particular word at hand. But we know, because we already have the topic assignments for all other words, and we assume the topic assignments for all other words are correct. We're trying to use that information to infer what should be the topic assignment for the current word lowercase w in the current document lowercase d. So that's the task. We have the exact formula as equation 1 in the appendix. But roughly the idea is, okay, again, if we just ignore the Dirichlet prior parameters alpha and beta, which you'll see next page or in the appendix, then roughly the current word assignment, topic assignment, is kind of based on the proportion of topic T, particular topic T in the document, and also the proportion or the probability of current word is going to be used in topic T. And you compare, because there are potentially K topics we can choose from, you do this calculation for each of the potential K topics, like topic 1 versus topic 2 versus topic 3, and all the way versus topic K, uppercase K, and you take the maximum across all the different numbers, and whatever the max number associated topic number will be the topic assignment for the current word W. So again, we do this for all the words in all the documents and for many, many iterations. Eventually, there will be almost or very little changes of the word assignments because the outcome, the distributions are already at their kind of steady state. So that means the algorithm has kind of converged to the optimal result, then we shall stop. But anyway, the equation for doing the update of the topic category for specific word is equation 1 in the appendix or next page. And after we're doing all this, and we also can kind of calculate for each given topic T, what are the word distribution, or given each document D, what are the topic distribution. This actually is our very original intention of doing the topic modeling, using computers to figure that out, answer the question of topic distribution without humans labeling or annotation. And again, the formulas are in the appendix. Let's take a look at those formulas quickly. So already skipped a lot of steps, but finally, so this equation 1 will be the one we use to assign the topic category for the current word. So it may looks like very confusing, but here, let me just call out something quickly. The alpha is one of the Dirichlet prior parameter. It controls the topic distribution per document prior, and beta is another prior parameter for the Dirichlet distribution, and this controls the topic words distribution. So if we just ignore the alpha beta, and this portion basically tells us, if you also read the description of each symbol, this portion pretty much tells us in the current document, which topic is more preferred. And this portion tells us, given the current word, what is its probability of showing in the particular topic K. Just we mentioned here. So this really gives us proportion of topic T in document D and proportion of word W in topic T, if we ignore the alpha and beta. So this is intuition, even though the whole thing looks pretty complex. And we're doing the update of each individual word in each individual document for many, many iterations. As we mentioned, eventually it will become stable. Then we stop there. So that's how we do the category assignment for word in the model kind of training process. And after that, then we'll have the equation 2 and 3 just to calculate the per document topic distribution or per topic word distribution. Again, the definition of each symbol have been laid out here. All right, now maybe let's walk through one example to figure out how the word topic assignment works in reality. Because the formulas here can be pretty confusing. But let's walk through one example to get the intuition. Let's see. We only have 2 documents. That's all we have. In reality, you may get hundreds, thousands, millions documents. But in our illustration, let's just work on 2 documents, and that's all we have. And when we combine 2 documents, make it also simple. We only have 5 unique words, and they're here. Word 1, word 2, 3, 4, 5. We only have 5 of those. And also in this simple example, we assume there are only 2 topic categories. The yellow D for dog and the green C for cat. So we only have 2 topic categories. And again, we're ignoring the alpha and beta. as we have seen on the previous page, so that the math will be a little bit simpler. So we get everything left is kind of word counts in a sense without alpha and beta in the picture. So basically we're using this formula for the example, but we're assuming the alpha beta are both 0, just make the calculation a little simpler. And also one thing to mention is this sign you probably know is proportion, because eventually the it's not like exact number, but everything is proportional. So everything scale up or scale down in the same ratio. So that's what proportion means. Anyway, this is the formula we're going to use where we assume alpha and beta both are zeros. All right. Again, now come to here. We also know that is we only have 2 documents, and we have put based on the random step and maybe based on certain updates, we already assigned the topics to all the words in document 1 and document 2. You see D and somewhere and CC somewhere in yellow or green. Only exception is this one. This word we put a question mark, and because this one is the word that we want to assign its topic category based on the equation 1 here by assuming alpha and beta both are zeros. All right. So that again, our task is to figure out what's the right category assignment based on what we have now. So we basically do some very simple word counting task. First, let's look at the document 1. If we look at document 1, go horizontally, all right, we can conclude that number of words in topic D in this particular document 1 have 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So pretty simple word counting. And also in document 1, the topic C, the green C, have 3 instances. So the simple counting. Now, next portion, we want to look across all the documents, both 1 and 2. And we figured out when we look across both documents, associated with topic D are as following. If something is under topic D and the first word, the word 1, have been used 4 times, 1, 2, 3, 4, and the second word have been used 0, because we do not see anything here, kind of blank means it's kind of a 0. And similarly, the word 4 have been used 4 times, and word 3, none of them is associated with topic D, so it's 0. And the word 5, 3 of them is associated with topic D. So that's very simple counting again. 4, 2, 0, 4, 3. If you look at what is being allocated to topic D within the document 1. Now we do the math. Okay, do the very simple. Actually, sorry, this part is across both documents. Now let's do very simple math. If it's a topic D, right? And what's the probability that it has, first word 1, and we know it's 4 divided by everything else, and 4, 0, 0, 4, 3, by sum of those numbers. So it's like 4 out of 11 it has word 1 for topic D. Similarly, we do topic C. We look across the 2 documents. We realize that first word is only used once under topic C, and the second word has been used 4 times under topic C, and third word has been used 7 times, and the fourth word has been used 0 times, and fifth word has been used 0 times for topic C. Now again, we want to know that given the topic C, what's the probability of containing the first word? And here is the simple math. 1 divided by sum of all the individual numbers. This is 1 divided 12, right? So far, so good. Everything we're just doing the simple word counting. Need a little bit caution, but this is basically how it works. And there's no complicated math here. We're just doing the counting based on the the description based on the rules here. So now question is, for this question mark word, okay, everything we have been doing here exclude the question mark word. Okay, now the question mark word should be allocated to dog or allocated to cat. So that's the question. What do we do? Well, let's see. Among all numbers we have calculated, those 4 are mostly important. So we also label them and give them different colors. Now the question is that a dog? Should be the category? Well, what we do is we take this number times this number, which give us 1A times 2A, and 9 times this number, basically give us 39 verse 11. Well, again, if you flip to the previous page, appendix, you pretty much realize we're using this formula by ignoring the alpha and the beta, by assuming alpha beta is 0. But we basically literally just applying this formula by doing the word counting. All right. Now we know that if assuming, okay, pretending this is dog, and 1A plus 2A based on formula will give us 36 divided by 11. And what about cat? Well, cat, you will get 1B times 2B, which is 3 times 1 divided 12, and this gives us 3 out of 12. This just based on the formula in the appendix, equation 1 in the appendix. And now you can see, okay, that formula tells us it's a proportion to category dog is 36 divided by 11. Proportion to category cat is 3 divided by 12. Compare this to, your answer will be, hey, the answer is category, for this question mark, I assigned the category to dog because this number is bigger than this number. And given all the information, topic assignments for all the other words across all the documents, it makes more sense to assign the question mark, this particular word 1 in document 1 into the dog category. So then this one will become the yellow D after doing all the calculation. So that is how it works. And again, appendix has the formulas. And yeah, basically this kind of concludes our today's class.